Dear students, today we are going to see the second half of the first module based on our syllabus. So let's go in deeper into the syllabus. As you can see, we need to study regarding Pentium class of processors, RISC and CISC processors architectures, then superscalar architecture and instructional pipelining, also branch prediction techniques and FPUs. Coming to the first topic, Pentium class of processors. So this Pentium class of processor or the series of processors which made a first remarkable introduction in the early 1990s. So why this Pentium class of processors they are getting this much hype? So we need to think about that. The reason is like it is having multiple performance enhancing features. What are those performance enhancing features? So they are the superscalar architecture, pipelining, branch prediction, floating point units. So these superscalar architecture, pipelining process, multitasking, so branch prediction FPUs, these all make them ideal for multitasking, multimedia as well as high level computing process. So coming to the launch of Intel, as I have already mentioned in the previous slide, like it was introduced in early 1990s. So actually it was launched by Intel, Pentium series of processors which was launched by Intel first in the year 1993, and it is one of the successor to the Intel 80486 processor, and it is widely used in personal computers during 1990s and early 2000s. So coming to the key features of Pentium class of processors. So basic key features are first one, superscalar architecture. So it is the first Intel processor to implement dual pipelines. So basically all the processor they are having a single pipelining mechanism, but here in the superscalar architecture, that is in Pentium class processors, we are having dual pipelines, that is we are having the U pipe as well as the V pipelines, and it can, because of that, it can execute two instructions per clock cycle with increased throughput. And this U pipeline handles all the instructions and V pipeline executes simpler ones in parallel. So these are the peculiar features of superscalar architecture. Now coming to the instruction pipelining. So as you know, like for executing each and every instruction, there are basically three processes. Okay, like fetch, decode, execute, like that. We have studied in the previous sessions. Okay, maybe in the previous semesters and all, we might have noticed this. These are the three phases of instruction pipelining. Coming to the Pentium class of processors, here already we told that we are having a superscalar architecture, and coming to the instruction pipelining, this is the first processor that introduced 5-stage pipelining in order to increase instruction execution speed. That is instruction fetch, instruction decode, address calculation, execution and write back. So which helps to achieve the instruction level parallelism and hence improving CPU efficiency. Coming to the branch prediction mechanism, early Pentium processors had basic branch predictions. Later versions like Pentium Pro onwards, which includes the dynamic branch prediction, which reduces the pipeline stalls or delays and improves performance in looping as well as the conditional branching code. Coming to floating point unit. Pentium class of processors, they are having an integrated FPUs which performs the floating point arithmetic, that is real numbers, and is faster, more efficient compared to the other set of earlier processors which we had like 80286, 386, 486, whatever it is. And it supports a complex calculation in both scientific as well as graphical and multimedia types. Also, another feature of this Pentium class processors is like it is having dual integrated pipelines, and it is having 64-bit address as well as 64-bit data as well as 32-bit address bus, which allows for faster memory access and data handling. And it is the first class of Pentium processor which introduced MMX technology. That is, it introduced multimedia instruction sets for faster processing of images, audios as well as video. So in short, we can say like Pentium class of processors are the advanced microprocessors which were introduced by Intel in 1993, and they feature superscalar architecture, dual instruction pipelining and integrated FPUs, and these processors significantly improve computational performance, which allows execution of 2 instructions per clock cycle and supporting multimedia applications via MMX. And this also laid foundation for the modern CPU design through enhancements like branch prediction and efficient memory caching. Mostly, modern CPU architectures are designed to balance performance, power consumption, and complexity. Among them, the most important design philosophies are RISC, CISC, and Superscalar Architecture. Like as in recent technologies, what we are doing is like most of the processors they are coming with certain uh, instruction set classification, and those instruction set can be either reduced one or a complex one or a superscalar type. Okay, so based on that, three different designs are there. First one is reduced instruction set computer, second one complex instruction set computer, and third one superscalar architecture. And each represents a unique approach to show how instructions are being processed inside a processor. Okay, so let's dive in detail regarding these three. So coming to the RISC, that is reduced instruction set computer, the basic RISC is like a definition of RISC is like a RISC is a CPU architecture. It's a CPU architecture which uses a small set of simple, highly optimized instructions which can execute very fast, usually within one clock cycle. Okay, so RISC is a simple CPU architecture which uses a simple instruction set which is highly optimized, which can execute quickly within one clock cycle. And the key features include, as I already mentioned, instructions are simple, so they are of fixed length. We can load or store architecture, only load or store access memory is there. Many general purpose registers are there for RISC process. It is easier to pipeline and is having a faster execution of instructions. So this is an example of RISC architecture. So it is having a simple instruction set which can execute quickly within one clock cycle. And certain examples of this RISC processors are MIPS, Spark, RISC-V processors. These are certain examples. Coming to the CISC, complex instruction set computer. So CISC is a CPU architecture just same as RISC. The only difference is like it is having a larger set of complex instructions where a single instruction can perform multiple low-level operations. Okay, so it can perform multiple low-level operations. The instruction set is not fixed as in the case of RISC. Here, the instruction set is complex and of variable length, and fewer instructions need to perform a task. Means a small set of instructions are used to perform some specified task. But this instruction sets are complex and is of varied length. And memory to memory operations are allowed. And since the instruction sets are complex, the pipelining is not that much easy. So it is harder to pipeline due to complexity. An example of CISC processors are Intel 86 processors family, example Pentium, then AMD processors. These are all examples of CISC architecture. Coming to a miniature version of the CISC architecture, it is having a microprogram control unit, then a control unit is there where through which the instructions are there accessed, and these instructions and the data path it is fetched by cache from the main memory. So here altogether the corresponding instruction sets are complex and of varied length, and it can perform a single instruction can perform multiple tasks. Okay, this is a case of a CISC processor. Coming to the superscalar architecture. So in superscalar architecture, it is another type of CPU design where the processor can issue and execute multiple instructions per clock cycle using multiple execution units. There are multiple execution units are there. Say for example, let us consider this as one execution unit that is for floating point, another execution that is for integer unit. So there will be similarly there will be a multiple execution units for the, and through this multiple execution units what is happening, multiple instructions are being executed, right? And the instructions are fetched and it will be there in the instruction queue. The later, based on the execution how it is being decoded, it will be dispatched using this dispatched unit. Okay, so this is the processor with two execution unit. There can be more than two execution unit in the case of superscalar architecture, right? So this is one such CPU design. And the key features include, it includes parallel instruction execution, right? And instruction level parallelism. The same concept is same only. So we can execute the instruction parallelly. That means instruction level parallelism is there, ILP. And it can operate either in dual or multiple pipelines, example U pipeline and V pipeline, which we mentioned earlier in the case of Pentium. So, and also it works either with RISC or CISC architecture. Okay. Now coming to the various examples of superscalar architecture using processors using superscalar architecture, that is Intel Pentium, that is the first superscalar 86 processor, uh, PowerPC, ARM Cortex-A processors. So these are the various examples of superscalar architectures. Coming to the comparison table, RISC, CISC as well as a superscalar. So first feature, RISC stands for Reduced Instruction Set Computer. Then CISC stands for Complex Instruction Set Computer. And regarding instruction set, in the case of RISC it is small and simple, while in the case of CISC it is large and complex, and in the case of superscalar it will either use this RISC or CISC based on the application. Coming to the instruction length, in the case of RISC it is fixed, and in the case of CISC it is variable, and in the case of superscalar it depends on underlying architecture. Coming to the execution time, in the case of RISC, one instruction per cycle, where in the case of CISC, one plus instruction, one plus cycles per instruction, because the instructions are complex, right? So more than one cycle is required to execute one instruction. Whereas in the case of superscalar, multiple instructions are executed per cycle. Okay. Coming to the memory access. So in the case of RISC, it is having either load or store data only. While in the case of CISC, it is having access from direct memory to memory. While in the case of superscalar, depends on the architecture. Coming to the pipelining, RISC is easy to implement. CISC, it's a complex due to varied length, and superscalar, it is having enhanced pipelining, like multiple pipelining is there because it is an enhanced version. Coming to the design simplicity, design is RISC is simple hardware, complex compiler, while in the case of CISC, it is a complex hardware and simple compiler. Where in the case of superscalar, it is a complex hardware with parallel units. And examples are, as we discussed, in the case of RISC, RISC-V MIPS. In the case of CISC, Intel 86 AMD. And the case of Superscalar, Pentium, PowerPC, ARM Cortex-A. And coming to the RISC, it focuses on speed and efficiency. CISC focuses on task reduction per instruction, and Superscalar, it focuses on the parallel execution and performance. So in short, we can say like RISC emphasizes simplicity and speed with fewer instructions, whereas CISC, it emphasizes powerful instructions that reduce code size and memory access. Coming to the superscalar, it focuses on performance through parallelism regardless of whether the instructions are RISC or CISC. So next topic is instruction pipelining. What is meant by pipelining? Pipelining means executing multiple tasks parallelly, right? So instruction pipelining is a technique which is used in CPU design where multiple instructions are overlapped in execution by breaking down the instructions execution process into separate stages. Like we know, like we are executing a particular data, we need to execute a particular instruction. What are the major steps involved in that? So we'll fetch one data, then fetching, decoding, as then execution. So first step is fetching, second step decode, third step execution. So once the data is fetched, the next step will be decoded, right? So after decoding, it will be executed. So instead of waiting for the entire process to get completed, what we are doing pipelining mechanism. While decoding the data, another set of data can be fetched, right? So that fetched data will undergo decoding in the execution phase of the previous data, right? Then it goes like that. This is known as instruction pipelining. Basically, this Pentium process, it is having a 5-stage pipelining which includes instruction fetch, instruction decode, execute, memory access and write back. Okay, so these are the 5 fetches or the 5 pipeline stages which are available in the case of Pentium. Okay, previously we explained with fetch, decode and execute. So here we are having 5 such pipeline stages. So what are the major benefits? It increases the instruction throughput and it make use of the CPU resources efficiently, right? And also enables fast execution. These are the major benefits. So this is an illustration of how a 5-stage pipeline process is being carried out. Consider the first case, first process like instruction fetch is there, like we'll fetch data from the memory. Then what we are doing is we are decoding those data, then executing, then we'll access the memory and put it in the memory and write back. Okay, so during the second stage, like there are 5 stages are there. During the second stage, what it is doing is it is decoding the first data, first instruction. During that time, it can fetch the another set of instruction, right? And during the execution phase, it will decode this instruction and the occurs a little delay like that and moves further. Okay, so if the number of cycles increase, number of instructions increase, what it is doing, stage by stage, it is fetching those data, decoding, executing, memory access, then write back. These processes are getting implemented. Okay, so this process is known as the pipelining process or instruction pipelining. So coming to the next topic, that is branch prediction. Pipelining improves the CPU performance by overlapping instruction execution. That is what we explained in the previous slide, right? So that is regarding instruction pipelining. So however, branch instructions are there like jump, call, return. They can disrupt the flow of pipelining by changing the control flow. So whenever a branch is encountered, following instructions in the pipeline may become invalid and they need to be flushed, wasting the clock cycles. So that is one of the major drawback in the case of branch prediction. So what we have to do, we need to properly enhance this branch prediction parameters so that the correct branch must be chosen. Otherwise, the instruction or the clock cycles will be wasted. So in order to enhance this branch prediction methodology, Pentium uses a dynamic branch prediction methodology in order to guess whether a branch will be taken or not. So if the prediction is correct, pipeline continues smoothly. If it is wrong, pipeline is flushed and restarted. This dynamic branch prediction methodology is implemented using a branch target buffer (BTB). It is a 4-way set associative cache with 256 entries, which stores information about recently executed branch instructions. So it is having a data regarding the recently executed branch instruction which contains a valid bit. It checks if entry is valid. It is having a history bit which tracks branch behavior, whether it's to be taken or not taken. It will have the source address as well as the target address, where source address is the address of the branch instruction and target where to jump if the branch is occurred. Now, how this BTB works? So it has a few stages, like the first one, monitoring. BTB is located next to the decode instruction stage. It watches for branch instructions. Then it will encounter first. That is, the new branch causes a BTB miss. Default prediction is not taken. Okay. Then what happens is the execution feedback, and the execution unit executes that particular branch. If taken, the next instruction is fetched from the target address. If not taken, then it will continue sequentially. Later it will update the BTB. If the branch is taken, BTB is updated with source and target and history bit is marked strongly taken, and later it go for the future prediction. When the same branch instruction appears again, BTB predicts based on the previous history using the history bit. In this way, the BTB works. So, in similar scenario, it can minimize the pipeline stalls and improves the instruction throughputs by accurately predicting the control flow. So, these are the concepts of branch prediction methodology. Next is the floating point unit. This FPU stands for floating point unit, which is a specialized part of the CPU design in order to carry out the arithmetic operations on floating point numbers. It is also known as the math coprocessors or numeric coprocessors. So as you know, these are the floating point numbers, which we are not going in detail regarding that. Usually, these floating point operations are complex and time consuming. If we go with ALUs, which is a general purpose one, which we usually use in processors. So, in order to reduce this time consumption and complexity, we go for FPUs, which accelerate the calculations involving scientific computations, 3D graphics, signal processing, and simulation and engineering software. So the Pentium processor has a built-in FPU. Previous version of processors like 8086, it is having certain external coprocessors for executing certain instructions, like 8087 will act as a coprocessor. We have already discussed like 80386, it is having a coprocessor like 80286, 287 or 80387, like we already discussed. We already studied the same, and it supports 80-bit extended precision registers, which uses a stack-based architecture with 8 registers, and it supports pipelining in order to improve the performance. Now coming in detail regarding the FPU registers. So FPU registers, it is having 8 floating point data registers from ST0 to ST07, which is organized as stack, and is having a status word register which stores condition codes like overflow, underflow, zero flag, etc. And is having a control word register which controls rounding mode, precision, and exception mask. So just have an idea of what are those things. So this table just brief you what are the difference between FPUs and ALUs. I think you will be able to grasp those ideas from this table. Okay, it is simple. So FP is for complex arithmetic operation and ALU for simple one. And FPU is faster, ALU is slower. Okay. So we can say like FPU is essential for efficient mathematical and scientific computation, and in Pentium processor, scientists tightly integrated with CPU in order to ensure fast and precise operation of floating point instructions. Here I shows one diagram regarding the FPU block. Like the diagram shows how FPU works to handle math operations like add, multiply, divide, etc. So we are using these three operations over here. So there is a PBX block is there. Instructions come from another unit, that this instructions to be executed will be come from the PBX unit, and thus if you input FIFO queue, that is a first in first out queue, these instructions stored in queue so that they can be processed in order. So if you pipelines, like it handles addition, multiplication, division, so similar operations it can perform, pipeline those operations. After pipelining, what it is doing, there is an FPU output arbitration. So this block decides which result to be sent first, and this result will be sent to the next unit, that is BPX. So this is a basic block of floating point unit. So with this we are winding up this session. So I hope you have got an essential idea on how this FPUs are like, what are the different Pentium processors, what are the different architectures we used, what is meant by pipelining, what is meant by branching predictions. Okay, thank you.